Hello everyone, I'm Alexander from Nanjing Foreign Language School, and today I will still be focusing on one typical physics problems from the 200 puzzling problems. And today I will go by problem 112. So there is a little green man found another asteroid with a radius of 10 kilometers and a homogeneous mass distribution. Well, they started to excavate and convey the material of the asteroid to the surface. The excavation of the metal was effected by boring shafts along a strip 1 meter wide around the equator of the asteroid until they had cut the asteroid completely in two parts. Then there's an accident. The prop separating the two hemispheres broke and the asteroid collapsed. The experts from this, a group, need to calculate the total force exerted on the props just before the collapse. Please help them. So the first thing I need to tell you is the surface gravitational field strength is G, like in the Earth. So because there's another problem in front of this, so that problem tells us about this information, but it doesn't matter actually. So when I first encountered with this problem, I will think of this. This is the original one, and when it collapses, it becomes something like this. It is not a scale. This is 1 meter, and the radius is of 10 kilometers. So I may think that, well, first I can calculate the gravitational field strength everywhere, and I will use calculus to calculate about the total force exerted on one part of the planet from another part. But this seems impossible because, first of all, three-dimensional calculus is way too complicated for us, especially in an interview. And the second, it is not very easy for us to get the correct answers. So we need to figure out another way. When you can't calculate the force in a direct way, you think of an indirect way. The first that we can think is, well, this is a width, so why don't we time it together? W equals IF times the width D. So W is actually the amount of work done to separate the two parts apart, and F is the attraction force on one part by another part. So now we just need to find W. But these things are a little bit easier. We can think about it in this way. So I assume that the part of this little metal is being transferred to the surface of the planet, and then it becomes evenly distributed. So I calculate the work force down. This is x, this is delta x. So first of all, we will calculate the density of the planet. Rho equals to m over v. It is m over 4 over 3 pi r squared per cube. And next we'll calculate about the g. So first of all, we will use the Gauss theorem to prove that gx equals to g times x over r, because this is a linear model. The Gauss theorem tells us that the sigma of all the charges inside over epsilon 0 equals to the total calculus of electric field length times ds. So it is very similar to the gravitational strength one. Just this becomes g, right? So we write another thing, and we can tell you that here the field strength only is dependent on this part. The outer part has no contribution to it. So it is actually a linear model, and you must have known that in the past problems. So now we will calculate about this delta volume. It equals to d times r 2 pi x delta x, and we'll calculate the delta mass. It is rho times delta v. So the delta work done to separate, I mean to move this part of the metal to the surface of the planet, equals delta m times, I don't know, some the gravitational field strength times distance. Because this is a linear model, so we use the average value to indicate the overall process, and we will do an average of them. That is 1 plus x over r over 2 times g. This is the average gravitational field strength times the distance. We can calculate by this. The overall work done, we sum this up, and we get about 3 mgd over 4 pi, r power of 4 here. And we calculate the right hand side using an integral. We will calculate this. W equals to 3 over 16 mg times d. So this may seem very hard at the first glance. Well, because we're not going to figure out the gravitational strength at each part and using some calculus to do that. But if we calculate the amount of work done to separate the two parts apart, that will be very easy. And you can see that every process is very straightforward. So you're going to do that actually, I don't know, actually very easily. I think it is a very brilliant interview problem. It don't require a lot of calculation, but the actually physics idea behind it is very amusing and intriguing as well. And I hope this problem finds well. And I also look forward to our next visit. So see ya.